Hey students, welcome to lecture number 4 of Linear Algebra 2. So today we want to talk about a matrix of a linear map. So last time we talked about linear maps and also about isomorphisms. And so let me recall a little bit. So if V is a finitely generated vector space, meaning we have a basis with finitely many elements, let's say V1 up to Vn. So the dimension of the space V is n. Then we had this coordinate map CB, so this map depends on the choice of the basis, which was a map from Rn to our vector space V by sending a vector lambda 1 up to lambda n to the linear combination of these basis vectors, meaning lambda I times Vi. And this was an isomorphism, and therefore when we have a linear map from the vector space V to some other vector space W, we will use this coordinate map to first translate, go back to the Rn, and also for W we can go back to some Rm, and then consider the linear maps between Rn and Rm, which are given by matrices. And then depending on the choice of these bases, we will assign to this linear map between V and W a matrix. So if we have a linear map between two vector spaces, linear map. So what we want to assign to this is some basis. So today, a matrix of F, whatever this means. And also one notation, so recall the inverse map of this coordinate map was given by this coordinate vector. So if this linear combination here is called V, then the coordinate vector of V with respect to this basis was just given by the inverse of this map, meaning this is just the tuple or the vector lambda 1 up to lambda n. Okay, so but first let us recall, if we have a linear map between Rn and Rm, what was the map, the matrix of this linear map? So this was a matrix. So this was an m times n matrix. So I was able to multiply this matrix with the vector in Rn and got a vector in Rm. And the column of this vector, so the first column was given by G of E1, where E1 was a vector 1, 0, 0, 0, 0. Then the second column was the image of E2. So this was this vector. And so on, up to the vector En, which had an 1 in the nth entry. And this image of G of this vector En gives the last column here in this matrix. So in these vectors, E1 to En are just one example of a basis for the space Rn. Okay, but this matrix in general doesn't make sense for an arbitrary linear map, because here we really used that the image of G of some vector is again a vector, so we could write this vector in a matrix. So to do this for general vector spaces, we need to use this coordinate map. So therefore here is the definition. So in the following, BV is the basis of the vector space V, and BW is the basis of the vector space W. And now we consider a linear map F from the space V to the space W. So here I have a linear map. And then the matrix of this linear map, which we denote by this. So the matrix of the linear map F with respect to the basis BV and the basis BW is given by the matrix of this linear map here. So let's make clear what this means. So because V has dimension n, because the basis has n elements, we have a coordinate map here from Rn to this vector space V. So this is the coordinate map CBV, so the coordinate map with respect to the spaces. But also for W, which has dimension m, because we have m elements here, we also have this coordinate map here, this CBW. And since this CBW is an isomorphism, we also can consider its inverse here. And now this linear map here, which says we first take the CBV, meaning we go first here, then we take F, and then we take the inverse of this. So this linear map is now a linear map from Rn to Rm. So this linear map is here. So in other words, we know what the matrix of this linear map is, because this is what we just discussed here. If we have a linear map from Rn to Rm, then we can make sense of this matrix of this linear map. Okay, so let's try to understand this a little bit more. So how can we actually write down this matrix here? So let's start with some vector lambda 1 to lambda n. So this is an element in Rn. So we start here now. So applying this coordinate map, this gives the element in V, lambda I Vi, and then applying F gives I to 1 to n lambda I F of Vi. So and here we use that F is a linear map. So F of this sum here, because F is linear, we can put F inside here. And now applying the inverse coordinate map here. So this just means taking the inverse of the coordinate map just means we can replace this F by its coordinate vector. So this is given by this linear combination here, where we have the coordinate vector of the vector F Vi. So this is an element in W. So we can ask for the coordinate vector with respect. Oops, so here it's just BW. So more precisely, what is if I start with some EJ? So EJ is a vector which has zeros, and at some point there's a 1 at the j's position. So this gets mapped to, well, everything is 0 except for lambda j, which is 1. So this gets mapped to Vj here, and under this map F, this gets mapped to F Vj, and under this inverse of this coordinate map, this just gets mapped to the coordinate vector of F of this Vj with respect to the basis BW. So now let's remember how to write down this matrix here. So again, the matrix of a linear map from Rn to Rm is given by this matrix here, where the first column is given by the image of G of E1, the second is given by the image of G of E2, and so on. And in our case here, this linear map here, let's call it G, the matrix of this linear map is what we want. This is the matrix of the linear map F. So the G, which is our F, which we want to calculate, Well, this is G of E1 here, and the last entry is G of En. And here we saw that Ej gets mapped to the coordinate vector of f of Vj. So this just means that this matrix here, the first entry, the first column, is the coordinate vector of the first basis vector with respect to this basis Bv, Bw, and the last entry is f applied to the last basis vector in V. Then this is an element in W, and we can ask for the coordinate vector with respect to the basis Bw. So this is just the formula to calculate this matrix of f with respect to these two bases. Okay. And so now some notation. So in this general case, we have two different vector spaces, V and W. But in a lot of cases, we will consider V and W will be the same. So in this case, if V equals W and these two bases are the same, so we actually just have one basis, so let's call it B. Then we also write that F is now a linear map from V to V with respect to this basis. By this we just mean that this is, with the definition before, the matrix of F from the basis B to the basis B. So we just write 1B here on the bottom right of this matrix. Okay, so let's do one example where we also have this case here. So this is example number 8. And this is quite similar to what we did last semester in Linear Algebra 1 and Homework 2, Exercise 3, even though at this point we didn't know what a linear map is for a general vector space, but there you were asked to write down exactly the matrix we are going to calculate now. So, oops. So we consider the map D, which we had before, in this case now from P3 to P3. So these were the vector spaces of polynomial functions of degree smaller or equal to 3. And we sent an f to its derivative. So f to f prime. And now we define a basis. We say that fix is just the monomial x to the power of I. Then the set, or the tuple f0, f1, f2, and f3, this is a basis, of P3. So and we can ask what is the matrix of this linear map with respect to this basis. So what do we need to calculate with the discussion we had before? Well, we need to calculate these columns. So we need to apply the linear map to our basis elements and then write this again as a linear combination in the basis and write the coefficients in this column. So again here we want d of f0, and for this we want the coordinate vector up to the coordinate vector of d of f3. Okay, so what is d of f0? Well, f0 is just the constant 1, and the derivative of this is just 0. And how do we write 0 as a linear combination of these f's? Well, it's just every coefficient 0. But now, what is d of f1? Well, d of f1 is just x, the derivative is 1, and therefore this is 1 times f0, so it's 1 times f0, 0 times f1, 0 times f2, 0 times f3. And then derivative of f2. So f2 is x squared, the derivative is 2x. So therefore this is 2 times f1. Well, here I was right, of x. So here it's this. And then, well, the last one is just d of f3, which is x cubed. Derivative is 3x squared. So this is 3 times f2 of x. So we get this matrix here. So this is the matrix of the linear map D with respect to the basis B. And of course, if you choose a more fancy basis for this space P3, then these matrices will look different. And now what we want to discuss is we want to talk about change of basis from one basis to another basis. So for this, let B1 be a basis of a vector space V and B2 another basis. So both of them need to have the same number of elements. And then we define the change of basis matrix from B1 to B2 to be, so we write denoted by S, B1 to B2. And by this we just denote the matrix of the identity map with respect to the basis B1 and B2. So in other words, this is just the matrix where I write in the first column, I take the first basis vector and consider the coordinate vector with respect to the second basis. And why is this a change of basis matrix? Because if I know this matrix, and I know, let's take V to be some vector in V. So if I know the coordinate vector of V with respect to the basis B1, and I multiply it with the change of basis matrix from B1 to B2, well, what I get, if you use the definition here, so this is B2 minus 1 CB1. So this matrix applied, well, what was the coordinate vector here? So this was just CB1 inverse of V. And here we will apply CB1 to CB1 inverse. So what we will just get is CB2 inverse of V. So this is just the coordinate vector of V with respect to the basis B2. So if I know the change of basis matrix and I know how to write my element in V in terms of this basis B1, then multiplying with this matrix will tell me how I can write this element in the basis B2. So in using this, we get some simple properties. So some remark here. So first notice that if I take the change of basis matrix from a basis B1 to B2, this is just the inverse of the change of basis matrix in the other direction from B2 to B1. And this is just clear from the definition here. And secondly, this is now, so in general, it's a long statement, but so if I have 4 bases of V and I have some linear map F from V to V, then if I consider the matrix of F from the basis B1 to B4, then what I can do is I change first the basis from B1 to B2, then I consider the matrix of F with respect to basis B2 to B3, And then I change the basis B3 to B4. So you always see that here I have the same. And then in the end, I get the matrix of F from B1 to B4. And this follows immediately from the definition. If you write these things out, you will see that you get exactly this statement here. But usually we will not consider 4 different bases. So in particular, there is a special case in which we will be interested most, will be just 2 bases usually, and one of them will usually be the standard basis, and then we will look for a different interesting basis and then apply this. So in general we will just have B1 and B2, and so if I take the basis of F with respect to basis B1, so remember this was just meaning that B4 equals B1, so this is just the notation that these 2 bases are the same. Then what I get is I can change from B1 to B2, consider the matrix of F with respect to basis B2, and then go back from B2 to B1. And this will usually be the case in our application. So now one reason why this could be interesting to do something like this, so to change the point of view of this linear map, is the following. So first let's do some short notation. Let's call this S. And here remember that, maybe let's write this out. So this is the same as the inverse of going from B1 to B2, F B2 S B1 B2. So let's call this matrix here S, then this matrix is S inverse, and let's call this matrix A. So this is just S inverse A S. And now notice, so what happens if I take the nth power of this F? So this means I take the nth power of this matrix here. And if I write this out, this is just S inverse A S one time, S inverse A S second time, up to S inverse A S. And here you see that these S and S inverse, so this just gives the identity matrix, so these cancel out. So in the end, I will just have S inverse A to the power of n times S. So in particular, if this A has a nice form, for example, if A is the diagonal matrix, let's say A is D1 up to Dm, and the rest is just a 0, then An is actually quite easy to calculate, because if I multiply a diagonal matrix with itself, I just need to multiply the elements on the diagonal. And therefore, if I'm interested in the nth power of this matrix, and I can write it like this, then I just need to know these matrices S and its inverse, S inverse, because this A is quite easy to calculate. And this is one nice application, or one reason to actually change a basis for a linear map to get an expression like this. And for this we want to do one explicit examples, which is given by Fibonacci numbers and counting bunnies. So for this, this is example number 9. So consider the following problem, which was proposed by Fibonacci in a few hundred years ago. So assume you have pairs of bunnies, and assume that after 1 month bunnies are able to reproduce. And now you start with a pair of bunnies and you assume that every time they are able to reproduce, they will create a new pair of bunnies. And now you ask yourself, if I start with 1 pair of bunnies, how many pairs of bunnies do I have, for example, after 12 months? So let's start here. So let's make a table. Month and bunnies or pairs. So in the first month we start with 1 pair of bunnies, and because bunnies can just reproduce after 1 month, they will not make a new pair after 1 month. Maybe let's make the bunnies a little bit smaller. So after 1 month I still have just 1 pair of bunnies. But now they are old enough to reproduce. So first, of course, we assume they don't die, so they survive. So here this is just they survive. But now they also reproduced and they made new bunnies. So let's say this is making new bunnies. So after oops, I made a mistake here. So after 2 months and 3 months. So after 2 months I have 1 pair, and after 3 months I have 2 pairs. So now after 4 months, this pair of bunnies, I mean they were already old enough last month, so also this month they make a new pair of bunnies. So let's make it like this. So they survive, but they also make new bunnies. And their children from last month, they are not old enough yet to reproduce. Oops. But they survive. So after 4 months, we have 3 pairs. And now, after 5 months, well, our original pair of bunnies, they survive, but they also reproduce. And so this pair of bunnies they made last time, they are not old enough yet to make new bunnies, so they just survive. But this pair of bunnies, which they did in the 2nd month, they survive, but they also reproduce. So this is survive, survive, and survive, but also reproduce. So after 5 months, we have 5 pairs. And now you can go on and ask yourself, if I denote by Fn number of bunnies, or number of pairs, after n month, then we see that in the 1st month it's 1, in the 2nd month it's also 1, but after this, in the nth month, I always have those coming from the month before, so the survivors, but then I also have the kids coming from those who are old enough, and old enough means they are older than 1 month, so they are the number of bunnies from 2 months before, so it's Fn minus 1. And here, of course, I mean minus 1. So and this is for, and here minus 2, sorry. And this is for n greater or equal to 3. So in month n, the number of bunnies are those from the last month, plus the number of 2 months before, because these are the ones who got created new. And now you can ask, what is the number of bunnies after, I don't know, 100 months? And then either you can count them, or you try to find a formula for this. So for this, now let's go back to linear algebra. So consider the following linear map. We denote it by f, which goes from R2 to R2, and which sends the vector x1, x2 to the vector x2, x1 plus x2. So what does this have to do with the problem? So let's start. What is f of 0, 1? Well, it's 1, 1. What is f of 1, 1? Well, it's 1 and then the sum of both of them, so it's 2. And what is f of 1, 2? Well, it's 2 and the sum of them, 3. f of 2, 3. It's 3 and 5. And so on. And you see that in general, if I apply f n times to this vector 0, 1, so if I do it n times, then the vector I get is exactly fn and fn plus 1. So this is also denoted by f. So this is just a notation for applying the linear map f n times. Okay. And now let's choose a basis and write down what is the matrix of this linear map. Well, in linear algebra 1, we usually just consider the standard basis. So let's say the standard basis we denote by B1, which is this one. So with this, the matrix of this linear map F with respect to this basis, well, it's just 0, 1, 1, 1. Because I just need to consider what's the first column is the image of 1, 0, which is 0, 1, and the second column is the image of 0, 1, which gets mapped to 1, 1. And our goal is to calculate this here. So in other words, what we want is so goal calculate this, which now just means that we take this matrix here, P1, and multiply it with the vector 0, 1. But, oh, and of course here we take this matrix to the power n. But if you multiply this matrix with itself several times, you will see that after several steps it's quite hard to actually give an explicit formula for this. And now the idea is to go back here to find a basis B2 such we can write our F, which is now written in the standard basis B1, as a matrix product like this, where this matrix here of this linear map F with respect to this new basis is maybe a diagonal matrix, because a diagonal matrix is quite easy to multiply with itself. And in this case here, I will just give this basis for you for free, and later we will learn how we can actually find these kind of bases when we talk about eigenvectors and eigenvalues. So the basis B2 we want to consider in this case is the following basis. It's 2 and 1 plus square root of 5, and 2 and 1 minus square root of 5. So first you can check that this is a basis of R2, which is quite easy to see. And then you can check that if we write the matrix of our linear map F with respect to this basis, so for this you need some calculation, but then you will see that this has actually this form: 1 plus square root of 5 over 2, 0, 0, 1 minus square root of 5 over 2. So indeed this matrix is a diagonal matrix, and you can also check, or this you can see directly by definition actually, that the change of basis matrix from B2 to B1, well, every time I change a basis from one basis to the standard basis, the only thing I need to write down is I just write the basis elements in the columns. So here I just write this. So this is the change of basis matrix from B2 to B1. And then we get, by what we discussed before, that F in our basis B1 is, well, first we can take the inverse of this matrix. So we take the inverse of the basis change from B2 to B1 because we want to go from B1 to B2. And then we take our F in the basis B2, and then we go back from B2 to B1. And this is nice because for this matrix here, we want to calculate its nth power, and calculating the nth power of this just means we need to calculate the nth power of this. And we saw here, if we have something like this, the nth power of this just means I need to consider the nth power of this matrix here in the middle. So the nth power of this matrix is this change of basis matrix, and then the nth power of this matrix, and the inverse of this matrix. But now we can write this out. So here it's just the matrix we see there on top. And now the matrix in the middle is just this diagonal matrix here. So the nth power is quite easy to write down. It's just 1 plus square root of 5 half to the power of n, 0, 0, and 1 minus square root of 5 over 2 to the power of n. And then you can also, well, this needs some work, but you can calculate the inverse of this matrix here. And you can check that this is just given by, where is it in my notes? This is 1 over 2 times square root of 5, square root of 5 minus 1 half, square root of 5 plus 1 half, 1 minus 1. So we have this. And, well, this looks a little bit complicated, but remember what we only want. So the goal was to calculate the nth power of this matrix times this vector 0, 1. So we would just need to multiply this matrix with 0, 1. So you see here it's quite easy to multiply this with 0, 1. Because here we basically just take the second column, get the vector 1 minus 1, and then we can multiply it with this matrix and with this matrix. So in total we get that if we multiply this with 0, 1, we get the following explicit formula. (1 over 2 to the n square root of 5), and here it's 1 plus square root of 5 to the power n minus 1 minus square root of 5 to the power of n. And the second entry here is the same as the first entry, where we just replace n by n plus 1. And remember, this gave the formula for fn and fn plus 1. So in other words, the number of pairs of bunnies after n months is 1 over 2 to the n square root of 5, 1 plus square root of 5 to the power of n, minus 1 minus square root of 5 to the power of n. And that's it. So we get an explicit formula for these so-called Fibonacci numbers. And so this is maybe just a silly example of these applications, but in general, a lot of applications are of this shape. For example, linear dynamical systems or some population growth, where you usually you have some matrix which counts maybe the number of population in a certain age, and then there's some matrix which describes the change of population from one group to the other, and you're interested how does this population behave after applying this matrix several times to see how the number of population grows. So if your population survives or dies out. And in these cases you always want to do something like this. So you want to calculate a big power of some matrix, and therefore you first want to change basis and try to find something like this. So you want to write your matrix as some product of matrices where the middle one is given by maybe some diagonal matrix, or even not diagonal, but a matrix where it's easier to multiply itself with. And yes, but this we will do in more detail when we talk about so-called eigenvectors and eigenvalues, because here the way to find this kind of basis is that these two basis elements are actually a so-called eigenvector of this matrix here, which just means if I multiply this vector with this matrix, then this will be just a multiple of this vector, and this multiple is exactly this number here. So you can check, if you multiply this matrix with this vector, you will get this number times this vector back. Okay, see you next time.